In this video, I'm going to show you a Python script Jason Hill developed for modeling the Monty Hall problem. We found Jason's blog post at the URL shown here, and he agreed to let us create this video based on it. In his post, Jason explains the Monty Hall problem and even shows you a mathematical proof of it using Bayes' theorem. In this video, I'm going to describe the problem to you and then walk you through Jason's Python code, which in addition to being a cool model, provides a good introduction to Python object-oriented programming. So here's the problem. You're on a game show, and you're presented with three doors. Behind one of those doors is a sack of money. You get to choose which door to open. Let's say you choose the green door. After you make your choice, the game show host opens one of the other doors to reveal that the money is not behind that door. For example, he might open the orange door, showing you that there's nothing behind it. Then he asks you, do you want to keep your choice or do you want to switch to the blue door? What should you do? Here's the model, and on Jason's blog post he has this all nicely commented. I've removed the comments so that the code is a little shorter and I can explain it as we go through. But this model has to simulate the act of hiding the money behind one of the doors randomly, and then the user selecting one of the doors randomly, so possibly the door the money's behind, possibly not, and then the game show host removing one of the doors that the user didn't select, and then the user choosing to either stay with the door he originally selected or switch to the door that the game show host didn't remove. This run game method at the bottom of the Monty Hall class will either return true if the user's door, the one that the user ends up selecting, does have the money behind it, or return false if it doesn't have the money behind it. So before we dig into the code here, I'm going to go run the program. So we'll create the class and we'll run the program. And in this first case, we're going to run it with the user switching every time. So you can see we're going to run this 1,000 times for I in range 1,000. And before that, we set wins and losses both to 0. M gets Monty Hall. So M is an instance of the Monty Hall class, and if m.runGame was switch set to true, so if that returns true, that means that the user selected the correct door, and we add 1 to wins. Else we add 1 to losses. Then we set %win to 100 times wins divided by wins plus losses. Wins plus losses will be 1,000. That'll be all the times that we ran it. Wins will be the number of times that the user selected the right door. We multiply that times 100 to turn it into a percent, and then we print out the results below. So let's do that. We're running this 1,000 times, and you can see the user wins 692 games and loses 308, so 69.2%. Let's run it again. This time 66%, this time 67%, and so on. So it's around 2/3 of the time that the user wins. Let's do it now where the user doesn't switch. You can see we set everything the same except switch is now false here. So we'll run it again, this one, and you can see the user wins 35.4% of the time, 33.5% of the time, 33.3% of the time. So in this case, if the user doesn't switch, he's winning about 1/3 of the time. So it looks like switching is the right thing to do. Let's take a look now at the class. So when we create an instance of the Monty Hall class, the first thing that happens is this init method runs. And in the init method, we set self.prizeDoor, that's prizeDoor of the instance object, to self.pickDoor. And Jason actually had this pickDoor method outside of the class. I moved it in the class just so it's all encapsulated together. Either way works fine. So self.prizeDoor gets self.pickDoor, and then we set default values of none for selected door and remove door. Then the run game method. That's the first thing we call, and remember this is going to return true if the user chooses the right door and false otherwise. So the first thing that happens in the run game method is we call select door. This is where the user chooses a door. And all select door does is make use of the pick door method to select a door randomly. So if we look at the pick door method, all that does is return a random integer between 1 and 3. It makes use of the random module, which we imported up on line 1. So self.selected door will get self.pick door, again, a random number, 1, 2, or 3. And then the user removes a door, self.remove door down in the run game method. Remove door picks a door randomly, 1, 2, or 3, and sets that to D. But then if D is the selected door, the one the user chose, or it's the one that the money is behind, the prize door, then we pick it again. So what this does is it makes sure that it removes a door that the user didn't select and does not have the money behind it. And then it sets self.remove door to D, whichever one was selected. Back in the run game method, we say if switch. So this is the first time we ran the program. We were switching every time. So if switch, self.switch choice. So switch choice, the method here, self.selected door gets 6 minus self.selected door minus self.remove door. So what's going on here? Well, there are 3 doors, and they're represented by integers, 1, 2, and 3. Right? And 1 plus 2 plus 3 equals 6. So we have a selected door, and we have a remove door. Those are 2 different doors. Let's say that the selected door is door 1, and the remove door is door 2. Well, 6 minus 1 minus 2 is 3. That gives us the other door, the one that wasn't removed and wasn't selected by the user. The same thing happens if we say that the selected door is 3 and the removed door is 2. 6 minus 3 minus 2 is 1. That gives us the door that the user didn't select and that the game show host didn't remove. So switch choice just switches the user's choice to the remaining door. And then finally, we return self.user_wins. And user wins just checks to see if the selected door is the same as the prize door. And if it is, it returns true. Otherwise, it returns false. And we can see from running the program again that the best thing to do is to switch. In this first case, if the user switches every time, he wins about 67% of the time, or about 2/3 of the time. So that's the model. Let's see if I can explain why this works in a simple way. If you want a more complex way, a real proof, you can look back at Jason's blog. But I'm going to try to present it to you in a more intuitive way. Here we have our 3 doors again. Now, imagine again that there's money behind one of those doors and you make a selection. Let's say you select the orange door. The game show host knows which door the money is behind. So he's going to open the door that doesn't have the money behind it. You have a 1/3 chance of selecting the right door the first time you choose. There's a 2/3 chance that one of the other 2 doors has the money behind it. The game show host knows which one does not have the money behind it, and he opens that one. So you selected the orange door. Let's say the game show host removes the green door. Should you switch to the blue door? Now, remember, there's a 2/3 chance before the game show host removes one of those doors. There's a 2/3 chance that the money is behind either the blue door or the green door. The game show host has a 100% chance of removing a door that doesn't have the money behind it because he knows which door has the money behind it. So he removes the one that doesn't have the money behind it. There's still a 2/3 chance that the money is behind one of those 2 doors, and you know which one it's not behind. So the 2/3 chance now is that the money is behind the blue door, and you should switch. This is a little easier to understand if there are 10 doors. Now imagine you select one door. Let's say you choose the yellow door all the way to the left. The game show host then removes 8 of the other 9 doors. Should you switch? Well, you have to ask yourself, why didn't he remove that orange door? Why did he skip it? And he skipped it most likely because that's the door the money's behind. Remember, the game show host knows which door has the money behind it. There's a 1/10 chance that you selected that door the first time. He removes 8 of the other 9 doors. There's a 9/10 chance that the money is behind one of those 9 doors. Of course, he's going to remove the 8 that it isn't behind. That 9/10 chance then all gets moved to that orange door. So there's the door that you want to choose. You definitely want to switch. And the same applies when there's only 3 doors, except that it's just a 2/3 chance that it's behind one of the doors that you didn't select. I hope that helps you understand the Monty Hall problem, and I hope you enjoyed the video. Big thanks to Jason for letting us use his post as the basis of this video. Check out his blog at the URL shown here.